let's get this day started on the right foot and give a big Kansas City welcome to Mr. Eric Schweikardt. Yeah, man.
Thanks, Jason.
Awesome.
Hi, everybody. Thanks for having me. I'm Eric, here in my capacity as Director of Modular Robotics. And that sounds a bit scary, a bit corporate, doesn't it? And if you'll humor me, I'm glad a couple more people showed up in the last 10 minutes. If you'll humor me, what's the best stuff to make robots out of? If you wanted to make some robots, what would you use to make the robots? Just shout out. Oh, louder, I can't even hear you. Anyone? Aluminum, plastic, all that stuff. Carbon fiber, all these things are good. It's a trick question. The best material to make robots out of are thousands and thousands of tiny little robots. Now, we've been doing this is not us, but academia and research has been making robots out of thousands and thousands of tiny robots for about 40 years now. There are all these great systems that are built. They're super cool. You see the videos online, self-reconfigurable stuff. But we've never found an application for this stuff. You see these academic papers. There's a paragraph called Applications just above conclusion, and it says, this is a great robot system. Everybody thinks there's huge promise with versatility and reliability and low cost. Maybe we'll end up using them in space or something. So we make robots out of thousands and thousands of tiny robots, and we came up with a few applications for what to do with them. So the first one is the idea of computational thinking. Traditionally, if you want to learn about loops and recursion and conditionals and networking and feedback and control and all that great stuff, you need to learn how to program. But about 8% of people learn how to program, and so that knowledge is encapsulated away from those people. And we thought kind of tiny robots would be a great way to help people understand those concepts. So I'm going to show you 3 systems today. The first one is called Cubelets. We've been making and selling Cubelets for about 5 years. It's a kit of these 40-millimeter little plastic cubes that you snap together and build robots with without any programming or without any wires. These are typical little creatures that kids build with Cubelets. Normally when you're building a robot, if you're a kid or an adult, you start by building a plastic and metal robot. That's the body, right? And then you shift your attention to a laptop and you program the brain. You program the behavior. That's Descartes, right? Mind, body, dualism. They're 2 separate things. But that's not how we work. Oops, sorry. That's not how we work. We're like closely coupled from shape and behavior. And that's how Cubelets work as well. There are a bunch of different Cubelets, and they're separated into 3 categories. Does anybody have a definition for a robot by any chance? What's a robot? Okay. The answer is a robot is any device that senses, thinks, and acts. And we can argue about that all night if we want. There are lots of competing definitions, but since you guys don't have any definitions to throw out there, that's our working definition today. So Cubelets are separated into 3 categories. Sense Cubelets, like light sensors, distance sensors, touch sensors, motion sensors. Thinking Cubelets, the colorful ones in between that do operations on data, like maximum and minimum. And action Cubelets, Cubelets that do things, outputs at the end, Cubelets that drive around, et cetera, et cetera. We make and sell Cubelets in a couple of different kits on our website and through Best Buy and Brookstone and places like that. And this is kind of an idea of how they work. That's a distance sensing Cubelet on the front that's now sensing the tabletop because it's pointed down. Since it senses the tabletop, it sends a high output value to its neighbor, the drive Cubelet, and the Cubelet little train rolls. When it hits the edge of the table, it sends a 0 value and the Cubelets stop. So the idea of a bunch of different little modules that you understand combining to create kind of a higher level behavior. You don't need to program with Cubelets, but you can if you want to. You can get a Bluetooth Cubelet, and you can snap it onto the system. And you can remote control your Cubelets robot from your phone, or you can do things like play Etch-a-Sketch apps where instead of twiddling 2 knobs, you're using distance sensors or yelling at your little robot to create drawings. Or kind of run some scientific experiments and use Cubelets as a data logger. Since you have a lot of sensors, you can snap them all together, run some scientific experiments, and see the output graphed on your phone. Cubelets. It's been around for a little while, and they're available online. And I think it's the first commercial robot system made of lots and lots of little tiny robots. Last November, we launched a second robot construction kit, with the idea of giving kids a model of complexity. So if you step back and blur your eyes and think about the world a little bit, all the biggest problems in the world, like social problems or political problems or environmental degradation, things like that, are the results of complex systems. Complex systems are systems that have lots and lots of little agents independently working, doing their thing, and when you step back and blur your eyes, you see emergent behavior. Right? So there's no such thing as society doesn't want me to be fat, because society doesn't want anything. There are lots of people that don't want you to be fat and lots of people that do, and it combines into this emergent behavior of feeling like society wants something. It's an example of kind of emergent behavior. There are lots of others, but that's another talk. So last November, we launched a second robot construction kit. This one's called MOS. It's not named after anything, and it's not an acronym. We just thought MOS is really cool stuff, because I come from a dry environment, Boulder, Colorado. And it's a second robot construction kit. The modules are smaller. They're 1-inch modules connected with these steel spheres in the corners. They're magnets on the corners of the modules and steel spheres, ball bearings, that connect all of the different pieces. It's also a robot construction kit. Kids snap together the stuff, build robots without programming, without wiring, without all of the things that are normally restricted to geeky white boys. This is the basic $150 Capreble Rongtron kit. And you can start to see how MOS connects and works. So the 1-inch modules have magnets in the corners, and the steel spheres, if you connect 1, you get a universal join. If you connect 2, you get a hinge. If you connect 3, you get a rigid connection. There are tons of different modules, just like Cubelets, of all sorts of different categories that do different things. And here we are building a little car with MOS. You've got motors and wheels and sensors and Bluetooth control. And the nice thing about the little steel ball bearings is that they give you all these cool kinematic primitives. Like you can make a steering box like this just by snapping together a couple of modules without having to deal with any gears or anything. So MOS is the second robot construction kit that lets you build all sorts of weird stuff without the programming, without the wiring. And you get some funny locomotion primitives. Stuff moves around. It's not all just cubes. It's amazing what you can do without programming. You know, normally programming is the code that runs everything, but this little creature was just put together with 2 distance sensors and 2 motors, and you get a little device that drives around and avoids bumping into walls. That kind of looks intentional, doesn't it? It looks designed. It looks like it's doing something on purpose. We have a tendency to look at things like that in the real world and think, ooh, that's magical, that's amazing. Somebody must have designed that. Now, we all really know that nobody's designed that life and creatures are all just emergent behavior from simple little components that we can all understand, but people have a hard time dealing with that. It's our belief at Modular Robotics that if we give kids tools to build their own little complex systems and watch behavior emerge in front of them, that they'll gain the intuitions necessary to see that type of behavior in life and not ascribe myths and legends to how it was created. MOS is also available right now. We did a Kickstarter. We raised $400,000. It was really awesome, and we fulfilled almost all of those, and you can buy MOS at Amazon and modrobotics.com. This is a bunch of kids playing with MOS, how it works. And just like Cubelets, if you want to extend MOS, the idea is that it's very low threshold, so kids can just jump in and start snapping things together. But if you want to extend it, you can snap on a MOS Bluetooth module, and you can reprogram or recontrol your robot. So you can program it with Scratch, just a nice little block-based language for kids who are just getting started with programming. Or you can also use MOS Flash, which is basically writing C code for your MOS creature. It's kind of a nice entry into programming for kids that want to, that are maybe a little disenchanted with pixels on a screen and want to play around with little robotic creatures. MOS. We think MOS is a great model for complexity, for multi-agent systems, and can maybe give kids intuitions about control and communication and all of those things, so that later on when they get to computer science class, it's just a description for concepts that they're familiar with instead of all new crazy stuff. Now, the really funny thing about modular robotics is that we assemble all of this stuff, we make everything in our little factory in Boulder, Colorado. There's 70 of us, and we work in a warehouse, and we make stuff in the USA, which if you ask anybody, the Consumer Electronics Association guy had to leave early, nothing like this is made in the USA. Stuff like this is made in China. And if you ask anybody, building a factory in Boulder, Colorado to make tiny robotic consumer products is asinine. And people have used that word a lot, actually, to describe what we're doing. But it's working, and I'll tell you why we did it. So a couple years ago, we took a venture capital investment, a few $1 million, and common wisdom said, go to China, find a contract manufacturer, spin up, get somebody else to make this stuff for you. So we got on a plane. A supply chain director and I visited 8 contract manufacturers in China, the top tier ones, the middle ones, the lower tier ones, Foxconn and AQS and Jetta and Early Light, all the companies that are making all of the stuff in your pocket right now. And it started to seem strange. And the thing that I realized on the plane as we were flying back from China on that trip is that there are 3 tiers of contract manufacturers in China. The tier 3 is a dirt floor contract manufacturer, and they're filled with people. There are like 4 people working every injection molding machine. There's one person putting in magnets, and another person pulling out parts, another person with a hairdryer getting the funny little white marks off it. At a tier 2 contract manufacturer, a nicer contract manufacturer, a more expensive contract manufacturer, there are fewer people on the line. There's a little more automation. And at a tier 1 Chinese contract manufacturer, there's nobody on the assembly floor. The lights are off. The assembly floor is dark. They don't even turn on the fluorescents. There's just this rhythmic buzz, click, whir of the factory running itself. Chinese minimum wage labor rates have doubled 4 times in the last 10 years, and Chinese hourly labor has gotten so expensive that most of the contract manufacturers, the biggest and best ones, in order to compete, are robotizing and automating their entire factories because they can't afford to pay. So it's still cheaper to have somebody in China make your stuff for you. But I think the trajectory doesn't show that that's going to be like that for a very long time. So we came back, and we made the rash decision to manufacture our stuff ourselves. It wasn't really a rash decision. We stopped everything. We took 8 weeks, and we built up this elaborate financial model, trying to assign dollar values to the soft costs of, it's really annoying to be on Skype at 1 a.m. every morning. Maybe that's worth something. People like made in the USA products. Maybe that's worth 1/10 of a percentage point of revenue or something like that. And built up this really elaborate model that convinced us, well, I was convinced, that convinced the rest of the team that we could compete. Not that we're cheaper than making stuff in China, but that we can be competitive. So problem 3 is figuring out how to be competitive. Chinese factories are robotizing and automating. Wait a minute, we make robots. Maybe we can kind of do this ourselves. So here we are. I mean, this is our funny little shop. We're moving into a big warehouse factory of the future soon, but this is our funny little shop with bikes hanging where a lot of people making $10 an hour are working in the factory. So of our 70 people, we've got about 50 elves. We call our assembly workers elves, and about 20 full-time salaried employees. And elves kind of run through this elaborate gamification system when they're building. You get points for every task that you do. You get bonus points for doing those tasks in a short period of time. You get 10 times bonus points if you break the speed record for assembling a certain task. And when you get certain levels of points, you level up. You become elf tier 2. You make an extra $1 an hour. You become elf tier 3. You make an extra $2 an hour, and you get a Modular Robotics t-shirt and a pint glass and a shot glass, and it's all gravy from there. But we're still paying 10 times what we would pay workers overseas to build our stuff, and that's unsustainable, and there's no way that we can compete. So allow me to show you for the very first time ever in public kind of a new system. Now, typically when you robotize or automate a factory, you buy a bunch of these things, $1 million robot arms and $2,000 PLCs and all this extremely expensive stuff. And that's necessary if you're a car plant. If you're swinging car chassis over a bunch of workers that, if you drop them, you'd kill a bunch of people, yes, you need the real stuff. If you're at one of those factories where if your line goes down, it's $1 million a minute, yes, you need all that real stuff. But we don't need that real stuff. We make robot toys. We have little plastic bits and circuit boards that we push stuff around in. It's really, really easy work. Allow me to present Farkas. Farkas is our third robot system. It's never been shown before in public. It's not for sale. It's the factory automation robotics kit for us. Not for the US, just for us, Farkas. It's also the name of the bad guy in A Christmas Story, which I think is kind of funny. Farkas is a little ecosystem. It's another robot construction kit made of lots and lots of tiny robots, but this one's for manufacturing, and it's to help us make our other tiny robots, robots to make robots. It's great once we're used to building robots out of lots and lots of little tiny robots to be able to leverage the same architectures and the same way of working to make these Farkas systems. I want to show you a couple instances of Farkas just to let you know exactly what we're talking about. This thing behind me is called the Cruzel. It looks like a slide projector carousel. Nobody in here remembers slides. Cruzel is carousel without the A, so it's the Cruzel. This is a hand-built thing that we built over the course of about 8 weeks, all laser-cut parts, 3D printed parts, stuff from the McMaster catalog. And this thing is designed to program and test little tiny circuit boards. So this thing came out of a need. We looked at our factory one day and we realized at one of the stations in our factory, we have these 4-foot by 8-foot plywood tables. There are 2 people, full-time, elves, sitting at that plywood table 40 to 60 hours a week, taking circuit boards, these little 2-inch circuit boards, out of a cardboard box, pressing them down onto a bed with spring pins on that programs and tests the circuit board. It takes 11 seconds each, waiting for a green light or a red light, and then putting the circuit board into the green box or the red box if it's a pass or fail. And when we realized that there were 2 people in our factory sitting there full time, mindless, dull, boring shit work testing these circuit boards, we thought, ooh, we can build a little robot to do that. So we built the Cruzel, and it's the first instance, it's the first little piece in the Farkas ecosystem. The Cruzel is totally hand-built. You can see it's a mess of wires on the inside. It's not a consumer product. It's just something that we hacked together. There's the carousel on top that you put a bunch of circuit boards in. There's a test mechanism on the bottom, and boards come out the other end. It is really nicely engineered, I won't lie. We have a bunch of great engineers at Modular Robotics, so it's tight and it's redundant and it's fail-safe and it never fails boards that pass. This is how it works. You pop in the individual test for the board that you're testing. We have 38 different circuit boards that we make at Modular Robotics. You snap the little boards into the top in the carousel. Green button means go, and the boards run through and get automatically tested and put in the right box. And one of these carousels takes about 26 minutes to run through the whole carousel. So now we have elves, and they have a bunch of Farkas units in front of them, a bunch of Cruzels, and they load them up, and they press all the green buttons, and then for the next half an hour, they go and they do something else. So this is an attempt at 10xing our productivity to be able to compete with manufacturing houses where labor is 1/10 of the rate. Farkas is really simple. It's hacked together. There are Arduinos in it and red boards, and it's just sort of thrown together like a little electronics project. And it's all totally modular. So to change the Farkas, the Cruzel, to do one circuit board to the other, as I mentioned, we have like 30-something circuit boards, you just need to make a new carousel for the top and a new test bed like this thing that slides in a modular fashion. The test bed has a bunch of these little sprung pins that makes contact with a circuit board and a bunch of special circuitry in it to test the individual circuit board that's being tested. And it costs us about $500 to build. That's not very much for factory automation robotics, not very much at all. Plus $8,000 or $10,000 in engineering hours, which is a lot of money. It would take us 187,000 circuit boards to be able to pay back the investment that we made in our first Farkas Cruzel. But when we make the second one, it only takes us like 2 hours of assembly time and $500. So after the second Cruzel, we only need to process 22,000 circuit boards, which we do in a week and a half at Modular Robotics. So these things start paying for themselves in a really rapid fashion. That's the Cruzel, first instance of Farkas. The second instance of the Farkas system is this thing, the Conveyance. And it's a mess of wires too, so I'm showing you a sketch of it first so you can actually tease out what's going on instead of looking at all the wires. It's a conveyor belt system with a bunch of modules along the conveyor belt system. Nests are little devices on the conveyor belt that hold our products, the orange pieces that make their way through this series of modules. And like the Cruzel is a circular conveyance, the Conveyance is a linear conveyance. This is a little mock-up showing how we want to do it. We wanted to make the conveyance robust and modular enough so that it could build cubelets, so that it could build moths, so that it could screen print t-shirts, so that it could build anything that we wanted it to build. And kind of this is the basic conveyance. There's a Geneva mechanism and a standard DC motor instead of really, really fancy, expensive motors. We're really trying to hack this together, as you can tell. And cubelets make their way down this line. And this is how you pop in modules. So individual little hot swap modules that do different things to the products as they make their way down the assembly line. You can just grab a bunch of different modules and stick them on there. I'll walk you through this next piece a little better. This instance of the conveyance that you see in front of you is for testing flashlight and distance cubelets. So you snap distance cubelets on, and that first module that's coming down and grabbing the cublet is called the waggler. And the waggler is designed to test the physical assembly of the cublet. Are there short circuits? Are all the power faces connected? Are all the ground faces connected? Et cetera. And it's waggling the connections to make sure they're robust. Then the cublet makes its way to the second stage. You can't see a module there, but there's just an Arduino there that's talking to the cublet, and it's in its microcontroller code. It's programming the cublet. Then the cublet makes its way to the third station, which looks like a waggler, but it's not, because you'll notice the faces are not waggling. And that one is making sure that the code that was just flashed into it actually works. So it's spoofing 6 adjacent cubelets and making sure that it's communicating well and functioning appropriately and passing data. And then the cublet makes its way to the fourth station, which has a little photoreceptor on it, and it sends the cublet a value, makes the light turn on, and then makes sure that the light is turning on at the appropriate brightness level for how it should function. So the idea is that we'll have 20 of these conveyances all around our factory and can grossly multiply the efficiency of our relatively expensive assembly elves. As I mentioned, Farkas is hacked together. You see a bunch of things from the SparkFun catalog and from the Maker Shed in here that you can easily buy for 20 bucks online. We use a lot of Arduinos instead of PLCs. This is a PLC. It's a programmable logic controller. If you ever go to a factory, you'll see these things sitting in front of the crazy robot arms that are swinging cars around. And they're $2,000 little boxes. They're usually made by Mitsubishi, $2,000 to $3,000 little boxes. And it's a little circuit board wrapped in plastic. It's the dumbest artifact from the 70s that still lives on, but is totally unnecessary. So instead of using $2,500 PLCs, we use Arduinos that we buy for 25 bucks, and sometimes we stick 2 Arduinos together so that we're totally redundantly redundant, and that's all great. It serves our needs. Sometimes we stack 3 Arduinos on top of each other. Cool thing about Farkas is that we're not selling it, we're not making it, we're just building Farkas for ourselves. So we decided to just open source the whole thing. So Farkas is open source hardware. It's just public domain. If you want to build a Farkas system to automate your factory, feel free. If you want to derive Farkas and do something and encourage local manufacturing for your basement or your manufacturing plant or whatever, just go online to farkas.org. You'll see a wiki. You'll see all of the CAD files. You'll see all of the bills of materials, all of the schematics, all the boards, all the code. And it's there for anybody to work on and build more instances of Farkas with the idea that maybe if we can have some low-cost factory automation, we can compete against sending everything overseas all the time. And I wanted to leave you with a note, with a quick thought on robots taking our jobs, because I hear that a little bit. I mean, I only hear that maybe 1% of the time. Usually it's robots that are going to come and kill us with their machine gun arms and lasers on their freaking foreheads and stuff. But it's a real concern, right? Robots are going to come and take our jobs. We hear a lot about jobs lately. We hear a lot about unemployment in the US. And we hear a lot about job creation in Kenya and Nigeria, and it sounds like we need jobs, right? More jobs, 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 jobs. And I guess that's true for anything but the very long term. And I'm kind of interested in the long term. In the longer term, I don't think we really need more jobs. We need prosperity. We need to be able to feed our families. We need to be able to live well. We need the money and the currency to do that. And right now, the only way to imagine doing that is through jobs. But I think it's kind of short-sighted to create more manual labor bullshit jobs for people, right? What we really need is prosperity. We can use robotics and technology to create the same level of prosperity that we can do if we have minimum wage workers working in our factories. We just need to figure out how we can take the resultant wealth, the resultant prosperity, and distribute it around so that it's not just the CEOs and the big robotics manufacturing companies that benefit from all the robotics technology. Good luck, right? This is America. We're never going to do that. I think that's a social and political problem that I fear that thousands of tiny robots can't even solve. Thanks.